Right, so 10 sharp. I would like to welcome team Alberta to the stage and start your presentation, please.
22,000 years ago, large parts of North America were covered by sheets of ice. The woolly mammoth roamed the earth. And humans, well, we had just started beekeeping. Our relationship with bees is so long and complex that it predates even agriculture. And yet, in recent years, this relationship has been put in jeopardy as the bees have begun to die. Hello and good morning. My name is Talia, and I'm a member of the University of Alberta iGEM team, and I'm here today along with my team members Ron and Jesus to speak to you about our project, the Bee Detector. Now, as I mentioned, humans have been keeping bees for thousands of years, and as a result, we are dependent upon them for our very survival. Today, bees pollinate 1/3 of our food, feeding 90% of the world's population, while fueling a multi-billion-dollar industry that provides thousands of jobs globally through bees' ability to pollinate while producing honey and beeswax. But in recent years, the survival of Apis mellifera, along with all other bee species, has become a source of concern to the international community as bees have begun dying at an alarming rate. In 2018 alone, beekeepers in North America reported losses up to 40% of their bees. To put that into perspective, a loss of 18% is considered to be the maximum amount that a beekeeper can expect without that being an abnormal number. And as researchers have warned us, we cannot ignore the death of the honeybee, because the loss of this important pollinator could collapse entire ecosystems, leading to the 6th mass extinction, not to mention the loss of that multi-billion-dollar industry and the thousands of jobs that it has created. So at this point, you're probably wondering, well, what's killing the honeybee? Through our extensive consultation process with beekeepers, we have learned that there are various factors affecting the honeybee. But particularly concerning is Nosema ceranae. Nosema ceranae is an intercellular parasite. The way it works is once the honeybee consumes the Nosema spore, it travels to the bee's midgut. From there, it causes an infection that spreads to the rest of the bee's body. This can lead to various debilitating effects, including changes to metabolism and cognitive function, and even physical malformations. And if Nosema doesn't kill the bee directly, then it's great at making the bees more susceptible to other stressors, including extreme changes to temperature, food shortages, and other diseases. This is what makes Nosema so scary for beekeepers, the fact that it makes the bees weaker to everything else that's affecting it. And this also has a disastrous effect within the hive. It's like a positive feedback loop that isn't so positive. The more bees that get sick and die, the weaker the hive is, and the more susceptible healthy bees are to infection. This can collapse entire colonies. This is what makes Nosema one of the leading causes of the reason why bees are dying. In 2018, Team UAlberta knew that we needed to take action. This led to the development of our project APIS, our antifungal porphyrin-based intervention system. Quite simply, the way it works is that we were able to develop a treatment using PPIX that could fight the Nosema infection within the bees. But after the Jamboree, the beekeeping community continued to reach out to us about our work, and we grew particularly close with the Alberta Beekeepers Commission. After presenting at their convention about our work on APIS last year, they approached us and spoke about a different issue that they were dealing with Nosema, the issue of detection. And since we've been asked by the community to tackle this problem, we knew it was too soon to turn away from the issue, because turning away from that would mean turning our backs on the entire beekeeping community. But of course, when deciding on and designing our project, we didn't just want to consult with one stakeholder. And so we spoke with beekeepers from across Canada, including Tim, Barry, and Stefan. And it was through this consultation process that we learned that detection of Nosema is an issue that is important to beekeepers everywhere. Because after all, if you can't detect something, then how can you treat it? There are currently 2 common methods used for the detection of Nosema ceranae. The first way is through visual detection. Using this method, beekeepers are told to look for the visual symptoms of Nosema, including declining populations, dysentery on the outside of the hive, and even bees having greasy-looking abdomens. Now, I don't know about you, but I don't think it would be particularly easy to see if my bee was looking greasy or not. And unsurprisingly, this is what every beekeeper we spoke to told us. They told us that this form of detection is inadequate, as often these symptoms are only visible once infection has reached a point where treatment would no longer be possible. This was confirmed by Courtney McInnes, a bee researcher who we spoke with. And as Tim, a hobbyist beekeeper, told us, this is also very scary because often hobbyists are just trying to help the bee population. However, they don't know what symptoms to look for, and as a result, these infections can get out of control and spread to other hives. This is particularly concerning, as Barry told us, a commercial beekeeper, because it can lead to the collapse of their entire colonies. Up to 40% of bees can be lost during a bad nosema outbreak. Now, if you are an experienced and wealthy beekeeper with time to wait, then you can access the second and gold standard method of detection, sending off a sample of bees for microscopy at a government or commercial lab. You heard that right. That's currently the gold standard of detection. And as beekeepers told us, unsurprisingly, this isn't enough because it's often costly, time-consuming, and as Stefan told us, it can take upwards of a month to receive results. So in response to the massive issue of detecting Nosema ceranae, we developed the Bee-tector, our easy and accessible on-site detection system for Nosema ceranae. I'm now going to pass it off to Ron, who's going to speak to you a little bit more about how we developed this system, not only through consultation with beekeepers, but through explicit collaboration.
So we wanted our detection method to be something that beekeepers can use out in the field. We learned through numerous consultations with beekeepers that they are very familiar with and would prefer using paper strip-based detection methods like pH strips, which they already regularly use for things like nectar and honey. We also learned that beekeepers are more than comfortable with crushing a handful of bees for a test, as at least 2,000 new bees are made each day. So what we wanted then for a detection system is something like a pH strip, where you get a sample of bees, you dip a paper strip into it, and then you check a signal to see if you have a nosema infection or not. So like a pH strip, our Bee-tector system is designed to be simple, familiar, timely, and field ready. But how do you actually even detect nosema spores? Unfortunately for us, the nosema spores are poorly characterized, which posed a huge problem for our detection system. However, our team took this challenge and we started our project using phage display, which allowed us to find novel ligands. Afterwards, we would use these phages and tag them with the chromoprotein to allow for the visual detection on our paper device once they have bound to the spores. So with all of these things in mind, we are able to split our main project into three main components, with these being the spore ligand, reporter phage, and the paper strip. The spore ligand is a part on the M13 phage that actually has a ligand that's specific for nosema spores. To find a potential phage ligand candidate, we performed a series of biopanning experiments using a commercial 12-mer peptide phage display library, and we then mixed it with our nosema spores. The power of this technique actually is that we are able to test many phages that have over 1 billion unique peptides at the same time. So to start these experiments, we got our phage library and mixed it with a purified sample of nosema spores. Afterwards, we would then wash all of these phages away, leaving only the bound phages and washing all the unbound phages. Afterwards, we'd use an acid to separate the bound phages from the spore and use these phages that have bound as the next input for the next round of biopanning. This allows us to continuously enrich our ligands, resulting in better and better spore ligands with each round of biopanning. Here are results from our third biopanning experiment, and each dot that you can see on the plate actually is a phage that was acid eluted from a spore. So each dot that you see here is a ligand candidate for our Bee-tector system. To verify that our phages actually didn't bind to uninfected honeybees and produce false positive results, we also performed a negative selection experiment where we tested the phages we got from our third round of biopanning, and then we tested it on a sample of a known uninfected bee sample. As you can see from this plate, no phages have bound to the uninfected bee sample, which shows that our phages are indeed specific to nosema spores. Moving on to the next component, we have a reporter phage, which has a tagged chromoprotein onto it to allow for the visual detection of the nosema infection once the phages are bound to the spore. However, we cannot directly express the chromoprotein on the phage, as this would directly compromise its structural integrity as well as its assembly. So to circumvent this, we further split this component into 3 smaller parts, with these being the phage spore ligand with an enzyme peptide tag, the chromoprotein, a modulin, also with an enzyme peptide tag, and then the sortase enzyme, which binds these 2 peptides together to result in a conjoined amodulin and phage particle. As part of our contribution to the wiki registry, we further characterized our amodulin chromoprotein for its fluorescent properties. So we did that to actually help in our B-detector quantifying our experimental process and production. We characterized the modulin for its quantum yield, its excitation, and emission properties, as you can see in that graph over on the right. We also actually modeled the visual signal resolution of the chromoprotein through a series of serial dilutions of the chromoprotein, as you can see on the left. Furthermore, we also contributed another part, adding a his tag to the amodulin part to the wiki registry. And this was done to purify pure samples of the reporter and to also verify that adding a his tag to the amodulin does not compromise its fluorescent properties. As you can see from the results on the left, we can see that we are able to purify the his tag amodulin compared to the non-his tag amodulin. And on the right, we can see that adding a his tag does not compromise the chromoprotein's fluorescent properties. This then takes us to the last component of our B-detector system, which is the paper strip, the part of the whole system that actually separates the bound phages from the unbound phages. This is a very necessary step because the unbound phages actually still produce a visual signal since they still have the same chromoprotein. So suppose you have no infection, the phages are able to elute all the way up onto the top of the paper, producing a dim but large band. If you do have a endostomach infection, however, these phages bind onto the spores at the bottom, and since they are heavier, they cannot elute as well. And the phages would produce a more intense band at the bottom, with the unbound phages eluting all the way up to the top. For a more severe endostomach infection, this band at the bottom would be an even stronger and more intense color. And in the lab, we worked on a few kinds of papers to test their separation components, and we picked the paper that was actually able to best separate the components of the crushed bees. We also tested multiple mobile phases for their polarities, and we even noted that the chromoprotein itself can elute in different ways with different mobile phases. So in conclusion then, the bee detector would work as this. The beekeeper would collect a sample of about a dozen bees from a hive, crush them, and mix it with our detector solution. Then he will dip a paper strip into the solution and then check to see if there is a endostomach infection. So, sounds pretty fine and dandy, but actually, having all of these tests run in a lab environment is not indicative at all of how it'll work in real life, out in the field. After all, our central end goal was to have the beekeepers in mind. So what our team did was we actually designed a protocol and a prototype for beekeepers to use. And we actually got the help of a local commercial beekeeper, Paul Christensen, to aid in testing out this prototype. Through watching Paul actually perform a prototype in front of us, he was able to provide really, really good feedback in our final product design and allow us to give us some insight that we had not even thought of before. One of the questions that Paul actually had was, how many bees will be needed to produce a visual signal? And so to address this question, we actually created a model, and I'll have Jesus here now to talk more about it.
We began our modeling journey by consulting the UAlberta iGEM team in a collaboration to gain more understanding about modeling and gather ideas on useful modeling applications of our project. We then decided to focus our project model on signal analysis. Based on the conversations with the beekeepers, we acknowledged that all of them advocated for a time-efficient on-site detection system to identify nosema spore counts in a simple manner. By characterizing our signal, we want to figure out how strong our ligands are, the detection limit of our system, and its correlation with the level of nosema infection. With this, we can provide the beekeeper with specific instructions as to what they should be looking at when using the bee detector, making our product as ergonomic as possible. From the biopanning experiments, we can provide a spectrum of visual signals indicating different spore counts. The beekeeper can then compare the paper strip with this visual spectrum to determine how bad of an infection there is. We know the minimum amount of spores that correspond to a diseased bee, so we wanted to investigate if our system can visually respond to that. Our variables are the number of chromoproteins per phage and the number of phages per spore. For the number of chromoproteins per phage, we are using literature values. As per the number of phages per spore, we are solving for a range, from the minimum, 1 phage per spore, to the maximum, the optimal number of phages that can spatially fit on that spore. This number was determined after a series of computations where we consider factors such as the surface area of the spore, phage dimensions, and volume of space available for the phage to bind. Our expected value will be anywhere in between, and so the goal was to be able to visually differentiate between the Amash-Lyme band containing unbound phages from the Amash-Lyme spore band containing the bound phages. We're inputting our value here to correlate it with the level of infection and then calculate the sensitivity of our detector. This helps us evaluate if our ligand is the adequate one for this specific application. Based on the titer assays, an acceptable ligand must be able to provide a ratio of phages per spore greater than 15 for us to be able to differentiate between the bands. However, the ideal candidate will provide a ratio closest to that of the optimal packing case. So, to answer Paul's question on how many bees are needed to detect the infection, our numbers are currently pretty high. However, to address this issue, we came up with potential modifications to improve the performance of our system. This included, but not limited to, using a reporter protein smaller in size with high visibility, along with the phage with highest binding affinity possible. Furthermore, the concentration of the bee detector can be increased by 100-fold to reduce the bee input needed to detect this infection. Aside from this signal model, we also want to investigate efficient methods on the production of our bee detector. And so we also model the kinetics around this process to compare different processing scenarios. Two of them were investigated, a simultaneous process and a sequential process. They both seem to work. However, a faster production rate of bee detector is observed on the sequential process. As there is a lot of improvement for this model, we envision to enhance its usefulness by including applicable variables such as diffusion times and control temperatures, for instance. So now we ask ourselves, is this bee detector really that safe to use? Well, to reassure the safeness of our product to beekeepers, our system will be providing a quenching solution with specific conditions to kill every single phage on the used paper strip. The beekeeper can then dip this used paper strip full of phages onto the solution to dispose it in a safely manner afterwards. Now let's hear more from Talia about our community engagements.
So this year we conducted various community engagements. We spoke with children at their schools and at their summer camps. We talked to people at the farmers market, and we posted weekly to our blog and podcast. But the interesting part of our community engagements is not what we told people, but rather what they told us. Through consultation with the public, we learned that there is a common concern about the use of GMOs, more specifically though, about GMO regulations within Canada. Rather than try and explain or educate away this issue, we decided to face it head on. This led to the development of our policy review. The purpose of this policy review was to look over Canada's GMO regulations and find where there was room for improvement. We then provided recommendations for how that improvement could take place without stifling scientific development. Some interesting findings, however, from our policy review is that Canada has not updated any of its GMO regulations since 2003, and it still allows for companies to do and report on all of its own testing. The next community that we wanted to have an impact in was the iGEM community. We were particularly interested in iGEM's demographics and inclusivity, and so we conducted our demographics and inclusivity survey. What we wanted to do with this was learn more about iGEMers' experiences. We collated this data and we used it to make a list of recommendations for how iGEM can become a more safe and inclusive place for everybody. All of this information can be found on our wiki. In summary, the bee detector and APIS can be used as a complete system to tackle the issue of Nosema ceranae, helping beekeepers in Canada and around the world. I would like to thank you all for your time and attention here today and welcome up my team for questions. Thank you.